Okay, second video for chapter 5, and we are doing this again. It's driving me crazy. Alright, use perpendicular bisectors. Well, you've learned how to construct a perpendicular bisector. You'll know it makes two lines can make four right angles, and it cuts the segment in half. So I can use perpendicular bisectors to solve problems for when you want to get some tea and crumpets. And I can find the circumcenter of a triangle. So there's going to be a new vocabulary word. In fact, there's going to be a lot of vocabulary words in this chapter. I'll do my best to kind of help you remember some little type mnemonics. All right, so first of all, we've got our little warm-up here. And if I'm going too fast, pause it, copy it down, and then listen, please. Solve for x. You will be doing this. All right, we have an x on both sides of the equal sign. So we're going to subtract the 8x on both sides. You get negative 5x equals negative 15. Then divide both sides by negative 5. X equals 3. Second problem. Maybe we'll work this one out on the side. 6x plus 3 is equal to 8x minus 14. Okay. Where's that glare coming from? I want to subtract 6x on both sides. Add 14 to both sides. And then divide by 2. Don't be afraid of a fractional answer. The next one, this one can be tricky, but you know what? If you draw a diagram, it'll save you. So M is the midpoint of AB. So I drew AB with M right in between. AM is 5x minus 2, and BM is 3x plus 6. Because it's a midpoint, set these two equal to each other. So I'm going to subtract 3x from both sides. You get 2x equals, and then add 2 to both sides. 8. So 2x equals 8. Divide by 2, you get 4. Be careful. Some students will stop right there. This is asking us to find AB. So take 4 and substitute it in. 5 times 4 is 20. Minus 2, you get 18. And again, don't stop right there. This side's 18, that side's 18, so the whole length of AB is 36. All right, so be really careful when you do those problems. All right, here we go. Here's our vocabulary. And I'll have to actually redraw what this picture used to look like because we'll be adding in. Okay, a segment bisector intersects a segment at its midpoint and cuts it in half. A segment ray, line, or plane that is perpendicular to a segment at its midpoint is called a perpendicular bisector. Okay, so we've learned that. Okay, so I'm going to draw my best. Let's say this is A, this is B, this is a perpendicular bisector, so it cuts it in half. So we're going to pick any point on this perpendicular bisector, let's say right here, and we're going to draw from each endpoint to the point on the perpendicular bisector. It just so happens that they will be the same length. If I pick this point and connect the endpoints to it, they will be the same length. If I connect one below it, let's go ahead and use this turquoise. Okay, now notice how we have 1 slash, 2 slash, 3 slash. You wouldn't normally put 4 slashes here. Sometimes you could just put the 4 there. Just make sure you know it's about congruent segment, okay? Because some individuals will think that's considered a length of 4. But usually we don't deal with more than 3 sets of congruent segments. All right, with the same measure. Okay, so here we go. Perpendicular bisectors theorem and its converse with an E. This is the picture for the bisector theorem. This is the picture for the converse. So be careful. Remember when we were talking about like parallel lines and alternate interior angles and vice versa. So in a plane, if a point is on the perpendicular bisector, like right here, then it is equidistant from the endpoints. So we're talking about this segment. So if CP right here is our perpendicular bisector of AB, then CA is equal to CB. Okay, so that's the picture on the left. Now how about the converse? So in a plane, if you have the congruent segments first, then you know that this is a perpendicular bisector. So it's kind of doing the opposite. So far, so good? All right. So example 1. In the diagram, WX is a perpendicular bisector of ZY. So that means this segment is congruent to that one. So set these two equal to each other to find WZ. So when we do that, we have 2x plus 11 equals 4x minus 5. I'm going to subtract 2x on both sides, so you get 11 equals 2x minus 5. Add 5 to both sides. 2x equals 16. X is 8. And again, don't stop right there. We want to find WZ. This is just x. So substitute it in. 2 times 8 plus 11 is 27. Okay. Example 2. So they did not show this perpendicular bisector going all the way through L, but pay attention here. In the diagram, QO is a perpendicular bisector of MP. So which lengths in the diagram are equal? Well, we definitely know MO and OP, these right here. And then because Q is on the perpendicular bisector, we know MQ and PQ. But look at this. The picture shows that these two are congruent. So that means this perpendicular bisector will go right through line L. Now, is L on QO? Yes, because of the converse theorem. So if they're equidistant, that means it's on the perpendicular bisector. So T is another point. Let's just put it right there on QO. Is MT congruent to PT? Yes. There we go. All right, little activity. Folding paper. Okay, so I'm actually going to do this one over. And I'm going to draw, and it starts right here. It's going to show you pictures of what you're going to be doing. And it's going to go on to the next page. Okay, so first we're going to draw a large acute scaling triangle out of paper. Fold it to form 3 perpendicular bisectors. Check the triangles and the perpendicular bisectors of your classmates. Okay, so we had a triangle here, or sorry, paper. Put it on white. Is that better? No, that's really bad. Okay, so we're going to draw our triangle. So we want an acute scaling. So I just got to make it acute. I don't know why this doesn't come out. Okay, so I'm just going to really make the endpoints heavy. And let me show you how this works. So for paper folding, if you want to make a perpendicular bisector, what I'm going to do is I'm going to fold this endpoint on top of that one. Okay, so can you see that sliding there? And now it's on top. Make sure your lines line up. I'm going to fold that. That fold is a perpendicular bisector. I'm going to color it in red so you can kind of see it better. Can you see it better? No. How about pencil? Yeah, this clicky pen has pencil also. Oh, you can definitely see that better. All right, now let's do this segment. I'm going to put this endpoint on top of that one. So hopefully you're doing this along with me. And we know the pencil will work, so we're going to color that in pencil. So far, so good. And now, let's map this dot onto this one, this endpoint onto the other endpoint. Make sure your dots are lined up and the lines are on top of each other. There's always a little human error involved, but do your best. There you go. What do you think? So now we've got to answer our questions. I've got human error here. Do all 3 perpendicular bisectors meet at a point? Yes, I'll just make that point really big so it looks like it. Label the vertices A, B, and C. A, B, and C. Okay, so far so good. Why is this weird? There we go, it's a little better. All right, and then it says, measure AP, BP, and CP. What do you observe? So I'm going to find out the length of each one of these. Okay, so P for the point of intersection. First I'm going to draw it. So AP, the length is about 4 centimeters. Let's draw BP and then measure it. It is about 4 centimeters. Uh-oh, what's going on here? And then CP, it's about 4 centimeters. Okay, they're all about 4 centimeters. So, what do you observe? It says same length. And is the point of concurrency always inside the triangle? No. In this one, it's going to be because we did an acute scaling triangle. So you're going to see in the future, or in a little bit coming up, what's going to happen if it was a right triangle or a obtuse triangle. Okay. My other example was much better. Worked perfectly than this one. Oh, just the shame. Okay, so here we go. Concurrency. When 3 or more lines, rays, or segments intersect at the same point, they are called concurrent lines, rays, or segments. The point of intersection of the lines, rays, or segments is called the point of concurrency. So you saw this in that activity. Now, what's kind of neat is concurrency of a perpendicular bisector of a triangle. Well, I went ahead and drew these. The perpendicular bisector made those right angles and cut them in half. I should mark those in, but it's not necessary. And then when you draw from each endpoint to that point of concurrency, okay, this is called the circumcenter, these are all equidistant. And it's going to become really important when you see that next drawing. Okay, so, but these are all equidistant. Okay, so here we go. Each forest ranger station is the same distance from the main office. Describe how to find the location of the office. So let's say this was station 1. I drew a triangle. Station 2 and station 3. So what you do is you find the 3 perpendicular bisectors. So I kind of did that lightly. This one goes like this. I guesstimated, okay? I didn't really actually construct it or fold it. So those are the 3 points. So the office, the main office, must be right there, because this distance, that distance will be the same. So vocabulary, here we go. The point of concurrency of the 3 perpendicular bisectors of a triangle is called circumcenter. Now think about it. Circumcenter means it'll make a circle outside that triangle. Look at this. We have an acute triangle, a right triangle, obtuse triangle. And when you find that circumcenter of each one, the endpoints will be on a circle with O being the center. The endpoints of the triangle are on the circle. Kind of cool, huh? And also, if you have an acute triangle, notice the circumcenter is inside. On a right triangle, the circumcenter is on the hypotenuse. And here, when you have an obtuse triangle, the circumcenter is outside that triangle. So as shown above, the location of the circumcenter, O, depends on the type of triangle. So the circle with the center O is said to be circumscribed about the triangle. Circumscribed means the circle goes outside the triangle. It's pretty cool. A lot of information right there. Now I know that this says right here, but on your picture it says obtuse. It's corrected. And how we can apply this. Here we go. 3 friends. I know the old one said Andrew, Jacob, Isaac. It now says Alex, Caitlin, and JD. They live in 3 different cities: Albany, Waycross, and Valdosta. This is in Georgia. They want to meet for tea and crumpets. Where should they meet so they have the same traveling distance? So you can kind of see I don't know if you can see the arcs. I have arcs here because I actually I went ahead and put arcs and constructed the perpendicular bisector. Remember? Arc above and below from each segment. And there's a little bit of human error. I was slightly off with that line, but if JD, Alex, and Caitlin all want to meet for tea and crumpets, the same distance will be at, it looks like Oscilla or Fitzgerald, somewhere out here. That's where they should meet. All right, so here is our homework assignment in the standards, but there are more pages. This is a nice summary of everything together, so you might want to earmark this, put like a post-it note on the side of this page. It puts everything together for you. We will be doing a project for Chapter 5. And then last but not least, I'm going to be hanging this up. Colorful Pretty Bird. It's kind of like a way to help us remember that the circumcenter goes with perpendicular bisector. Colorful Pretty Bird. Okay, this will be hanging up in the room. Everybody have a really nice evening and go Indian Trail Volleyball tonight.